Okay, should be recording. Today I want to look at some transformations between two different coordinate systems, and saw a little bit of a hint yesterday in that video I showed you that simultaneous events won't be recorded as simultaneous in different reference frames necessarily. And so we'll do an example problem with that today. But first, I want to start with something called the Galilean transformations. And what we'll have is two coordinate systems. We'll have an S coordinate system, which is our usual X and Y coordinate system. And then we'll have a reference frame that's moving with respect to that. And this other coordinate system will be an S prime system. And it has an X prime coordinate and a Y prime coordinate, and presumably it would have a Z and Z prime coordinates that are coming out of the board or out of the page at us. But the primed coordinate system is moving to the right with respect to the unprimed coordinate system. And so I'm going to start using the letter U to stand for the speed between two different coordinate systems. And actually, we could think of it as a velocity. And if we put a minus sign on it, we'll have it going in the other direction. But at time zero, the two coordinate systems coincided. And so the distance from the y-axis in the S system to the y-axis in the S prime system is UT. And if we consider the Galilean transformations, and one thing we'll say is that at t equals t prime is equal to 0, we would have that x equals x prime, y equals y prime, and z equals z prime. Can't see the z coordinate system, but that's okay. So what happens at later times? Well, there's nothing going on in the y direction, so that'll always be equal. We'll have y equals y prime. There isn't anything going on in the z prime in the z direction either, so z is always going to equal z prime. And then in non-relativistic situations, there's going to be no difference in the passage of time between the two coordinate frames. But one thing is that x prime, if you pick some point in space, like this one could be x prime, y prime, like that, the x prime coordinate system is going to equal the x coordinate plus or minus ut. So x prime will equal x minus ut, or you could think of x equaling x prime plus ut. So this distance plus this distance will equal the distance from the origin of the x coordinate system. So those are the Galilean coordinates. Now, we're going to try to develop some coordinates that are relativistically correct. And these were worked out by a physicist named Lorentz. Let's see, his first two initials were AE, and I think he just went by AE Lorentz. I don't know that he ever, that I've ever seen his first name, but it might be Alfred or something like that. Who knows? Anyway, he was a contemporary of Einstein's, and he looked at the relations that Einstein had developed for special relativity and figured out these transformations. And so a lot of the things you see having to do with special relativity weren't necessarily worked out by Albert Einstein. Some of them were worked out by his contemporaries who were looking at it, at the consequences of what he'd done. However, the relativistic transformations are going to look different, and as you might imagine, there will be a factor of gamma that shows up in these things. The first one, below the dashed line, is going to be the relativistic expression. So the first one you could get would be x is going to equal gamma times x prime plus ut prime. Okay, all of a sudden, we're going to have to distinguish between time and the two different coordinate systems. Something else we can say is that t, the time measured in this unprimed coordinate system, will equal gamma times t prime plus ux prime over c squared. And I'm not going to try to develop these for you. We'll just accept that Lorentz figured these things out. And then we'll also have y is going to equal y prime in the directions perpendicular to the velocity. There isn't any change in the things. And so similar, z will equal z prime. We're not going to do any problems dealing with z, so we won't be adding with that. Occasionally, maybe we'll deal with one that deals with y prime. I think we've got one we'll do today, but most of the time we won't. And then there will be kind of inverse transformations. The x prime transformation will equal gamma times x minus ut. You notice we had x prime plus ut prime. Here we've got x minus ut. Now, we have a velocity that's taking the primed coordinate system to the right toward the positive x direction. We could have it going in the opposite direction, in which case the u's would end up getting, or the terms that involve this would have have their sign switched, basically. So this would become a minus and this would become a plus. Okay, we already knew that y prime is equal to y and z prime is going to be equal to z. Time-wise, we'll have t prime equaling gamma times t minus ux over c squared. So they look similar, but they've got their signs switched on the things there. And the prime things are both in terms of the unprimed things, the t and the x, and the unprimed things, x is in terms of x prime and t prime. So that's what these are going to look like. And we'll do some problems that deal with this, but we're also going to deal with velocity. And we're going to do several examples dealing with velocity transformations and see what happens. If you imagine that there was a coordinate system, like maybe a rocket ship that was moving away at 3/4 of the speed of light, and it launched something moving away from it at half the speed of light, according to the Galilean transformations, the speed relative to this thing would be 3/4 plus 1/2 would be 1 1/4 times the speed of light. But we'll find out that doesn't happen. That no matter what we do, we always end up with a relative speed between two things that's going to end up being less than the speed of light. Pretty close to it sometimes, but we'll see how that works out in the transformation. But the way we'll get the velocity transformations is to take differentials of this x prime and this t prime. And if we do that, let's see, I think maybe I'll do it on a piece of scratch paper so we can just write the result down underneath here. I take dx prime, the differential of x prime. Well, gamma is a constant, u is a constant, but x and t can change. And so I would it'll be gamma times dx minus u dt. And so that would be the differential of x prime. The differential of t prime, dt prime, is going to equal, well, what can change in here? Gamma won't, u won't. We're assuming constant speed, relative speed between the two coordinate systems. C won't change, so it's just t and x that changes in here. And I would get gamma times dt minus, let's see, u dx over c squared. Okay, and then from that, I can figure out dx dt prime, dx prime over dt prime, which is actually going to be v sub x prime. Okay. Well, I just take this and divide it by that, and so I'll have gamma times dx minus u dt divided by gamma times dt minus u dx over c squared. And if I multiply top and bottom by 1 over dt, and distribute it through those parentheses, by the way, the gammas will divide out, so those are gone. I would have dx dt on the top minus, when I multiply this one by 1 over dt, I just get u. And on the bottom, let's see, I would have 1 over dt times that is going to be 1 minus u over c squared and dx dt again. Now, dx dt is going to be v sub x, so this ends up being v sub x minus u divided by 1 minus, let's see, it's going to be u v sub x over c squared. Okay, this is the velocity as observed in the primed coordinate system. And if you think about it, let's see, the v sub x minus u, well, here's something to imagine. Let's suppose that the primed coordinate system is a train car that's moving to the right with a speed u. Okay, and somebody on the ground, or actually imagine that, yeah, somebody on the ground manages to throw a baseball that's going faster than this railroad car happens to be. So it throws it with a speed that is, maybe this thing's only going 30 miles an hour, and a baseball pitcher throws a pitch that's going 90 miles an hour. So what you would observe on the railroad car is that that pitch is only going 60 miles an hour with respect to you. It was going 90 miles an hour with respect to the ground in the same direction you're traveling at 30 miles per hour. So that baseball is going to catch up to you and be going faster than you by 60 miles an hour. That's what the numerator represents, is the Galilean transformation. But what we've got on the bottom is something that's going to change that. And so, and it's not going to change it by much if the speed isn't much compared to the speed of light. So it's only when these speeds are comparable or reasonable fractions of the speed of light that this denominator is going to make much difference. And then we can do a little bit of algebra and solve for v sub x prime here. But before we do that, or v sub x, before we do that, let's go ahead and let's see. Solve for this. V sub x prime will equal v sub x minus u over 1 minus u v sub x over c squared. So that's our transformation of one of the velocities. And by the way, if the two things are moving together, then you'd change the sign on the terms that have u. So we might run across an example like that. But let's go ahead and see what happens if we solve this for v sub x. And the first thing I'll do, since I have v sub x prime is going to equal v sub x minus u. I guess I could do it with the differentials again if I wanted to. Yeah, I could do it with differentials, but let's go ahead and do it with just algebra. V sub x minus u over 1 minus u v sub x over c squared. Multiply out from underneath by that, and I'd get v sub x prime minus u v sub x prime over c squared is equal to v sub x minus u. If I get the terms that have v sub x in them over to one side and other things on the other, so v sub x prime minus u will equal u v sub x. Yeah. V sub x prime over c squared plus v sub x. Whoops, that should have been a plus u. Okay, so factor the v sub x out of there. On the right side, v sub x prime plus u is going to equal v sub x, and I'm going to reverse the order of inside here. 1 plus u v sub x prime over c squared. And then I just solve for v sub x. And v sub x will equal v sub x prime plus u divided by 1 plus u v sub x prime over c squared. And so that's the reverse transformation, and it looks an awful lot like that one. I just swapped the prime terms for the unprimed terms and changed the signs on u. So, but we'd have v sub x is equal to v sub x prime plus u over 1 plus u v sub x over c squared. Okay, so that's our full set of transformations for the Lorentzian transformations. And now let's try to apply those things. And I think I'm going to keep this sheet handy, and I'll keep dropping it down over these things as I'm solving problems to see how we should use these things. Okay, that was just white paper. What did I do with the problems I printed off to do today? Oh, here we go. Okay, suppose the S prime system is moving to the right at 0.55 C. Okay, well, that sounds an awful lot like the situation that we have here. The S prime system is moving to the right at 0.55 C. In this case, U is going to equal 0.55 C. So that's what we've been calling that. Two events occur in this system, that's the primed system, which an observer in the S prime system judges to be simultaneous. One event occurs at x prime equals 0, the other at x prime equals 4,500 meters. The two events are said to occur at t prime equals 0 by observers in the S prime system. So these two events happen at t prime equals 0, and they happen at x prime equals 0 and at x prime equals 4,500 meters. Let's see, determine when each of the events occurs according to an observer in the S system and the time interval between the two events, and which event occurs first. Well, there's one thing they don't give us, and that is maybe it doesn't matter. But let's see. X is going to equal that one that happens at position 0 and time 0 is going to also happen at x equals 0. The one that happens at time 0 and that other thing is not. So let's see how this works out. One thing we're going to need for this, well, I'll just go ahead and write down the two things. X will equal gamma times x prime plus ut prime, and t will equal gamma times t prime plus u x prime over c squared. So we're going to have those things going on. Oh, one thing we're going to need is gamma. So gamma in this case is going to be 1 over the square root of 1 minus u squared over c squared. I know I've been using v for that, but we can switch to u some of the time. So anyway, and that's 0.55 c. So we're doing turn on calculator. There we go. And since u is equal to 0.55 c, I just have to, I can say that beta is u over c. It's going to be 0.55. So I just have 1 minus 0.55 squared in here, and I get 1.20 for gamma. Okay, well, let's see. Let's pick the one that's happening at event at x prime equals 0. Okay, the time that happens, yeah, it's just asking when each of the events occur, and so we don't have to worry about the other thing. T will equal gamma, which is 1.20, times t prime, which is 0, plus u over c squared, which is 0.55 c divided by c squared, and then times the x prime position, which is 4,500 meters. Okay, well, one of the c's divides out, so I'll just have 0.55 times 4,500 over c. The time in the unprimed coordinate system for that event. Whoops, this was the event at x equals 0, so this is 0. Time is also 0. Okay, they both agree about that one that happens at the origin. But let's figure out that event at x prime equals 0. That was the one that I actually started writing down the thing for here. Event at 4,500 meters. Okay, well, that's going to happen at a time of 1.20. That's my gamma. T prime is 0. They said it was simultaneous. And then I'll have 0.55 c for u, 4,500 meters for x prime, and c squared. Okay, so now I can try to figure this thing out correctly. And I'll actually end up with 1.20 times 0.55, a dimensionless quantity, times 4,500 meters divided by the speed of light, 3.00 times 10 to the 8th meters per second. And I guess that's all in one set of parentheses there. So okay, and I get at a time of 9.9 times 10 to the minus 6 seconds. Okay, but it's not zero. And we're talking about not that far apart, 4,500 meters, and happens 9.9 microseconds later. So the event that occurs first is the one that was at the origin, but they'll say that other event occurs later. Let's see. If the S prime system is moving to the left at 0.55 C, when would an observer in S say they occur, and which event would occur first? Okay, well, if it's moving to the left at 0.55 C, the only thing that changes in these things is the sign on U. And so the observer in S would still say that first event happened at time zero, because you've got a zero here for the time it occurs, and you've got a zero for the position it occurs. So that's not going to change. But for the other event, we'd have a minus sign here. And so you'd be getting a negative 9.9 times 10 to the minus 6 seconds. That observer in S would say that the event out there at 4,500 meters occurred first before t equals 0. So that's what's going to change on here. And these things are kind of weird, but you have to just kind of plow through and trust these relations and see how things go with them. Okay, let's try another one. An observer in frame S prime is moving to the right, this time at a speed of u equals 0.600 c, away from a stationary observer in frame S. The observer in S prime measured the speed v sub x prime of a particle moving to the right away from her. What speed v sub x does the observer in S measure for the particle if A, v sub x prime is 0.400 c, B, v sub x prime equals 0.900 c, and C? So this is a chance to explore those velocity transformations. And here's the one that we'll use. We want to know what the observer in S happens to measure for the speed of the particle. So we'll be using v sub x equals v sub x prime plus u divided by 1 plus u v sub x over c squared. All right. And what we have here is that u is 0.600 c. And we've got these various quantities for v sub x prime. So for A, we have v sub x prime equals 0.400 c. Now look at the numerator, v sub x prime plus u. Or actually, yeah, look at we're after the v sub x here. V sub x prime plus u. Well, there's v sub x prime. Here's u. Those add up to 1.000 c. So, which is exactly the speed of light. But we're going to be dividing by 1 plus u is 0.600 c. v sub x, that's supposed to be v sub x prime there. Yeah, when I wrote this down, I didn't have it correct. It's supposed to be v sub x prime. Yeah, doesn't look much like a prime. Anyway, v sub x prime is 0.400 c. And then I'm dividing by c squared. So you can see the c squareds divide out here. And 0.6 times 0.4 is 0.24. So I'll have 1.000 c. The significant digit remains in the thousandths place, but I'm not going to have that much on the bottom. And then 1.24 with only, actually I'll have 1.240. So I'll get 3 sig figs on this. But it's not going to be the speed of light. Faster, yeah, it's going to be smaller than that. And that's just something that happens. And I get 0.8 806. So v sub x equals 0.806 c. So I guess you could call it 0.8065, but yeah, we could stick that in there. Anyway, 0.8065 c, but it's not going at the speed of light. So it got closer to it, but did not exceed it. So let's see what happens when it's going v sub x prime is 0.900 c, and then that other one there. Well, v sub x will equal the sum of those two velocities, just add them together, where is it, 900 c, 0.400 c, and our numerator is going to be 1.300 c divided by 1 plus 0.900 c times 0.4. Yeah. It's 0.600 c that should be up here. Because that's u that's supposed to be up there. Yeah. Remind myself of that every time. Okay, 0.9 plus 0.6 looks like 1.500 c, and the uncertainty stays in the thousandths place for the numerator. 0.900 times 0.600 is 0.540 c squared. So on the bottom, we'll have 1.540 to 4 significant figures. And again, this thing's bigger than that. So we're not going to be going the speed of light still, even though that thing's leaving the primed coordinate system at 9/10 the speed of light, which is moving at 6/10 the speed of light away from the unprimed system, still doesn't happen. So let's see. I get 0.9740 C. So here's a place where the number of significant figures is actually bumping up by 1 because we've got things added together, and that lets you do it. Here we'll have 3 significant figures, but they're all to the right of 1, and this is exactly 1. So that's how we do that. So anyway, still not going the speed of light, and it won't happen here either. Let's just see what happens there. V sub x will equal v sub x prime plus u. So 0.990C plus 0.600C all over 1 plus 0.900C times 0.600C. Whoops, 0.990. Excuse me. I had it on right on top over C squared, which ends up being, well, let's see. I think that's 1.590, if I remember right, or figured it out right. Divided by 1 plus, the C's divide out. Yeah, this bottom down here ends up being 1.594. So we'll have 1.590C divided by 1.594. So we're getting closer, but still don't get there. 0.9975 C. So, whoosh, still didn't make it. Okay, well, let's try another problem. Some kind of a weird transformation on this next one, I think. Yeah. A moving rod is observed by someone who sees it as a moving object. So you have this rod that's at an angle here, and that's the direction of motion. And it's observed, you think it has a length of 2.00 meters, and it's oriented at a 30-degree angle with respect to the direction of motion. And it has a speed of 0.995 C. So, question is, what is the proper length of the rod? And what is the orientation angle in the rod's rest frame? Well, here's the thing. We can think of the rod as having two components. It would have an L sub X component and an L sub Y component. Okay, that's going up that direction. And what you're seeing, actually, this is L sub X prime, and L sub Y over L sub X prime would equal the tangent of 30 degrees. L sub Y is going to equal L sub Y prime. So that component is not going to change. In fact, L sub Y prime over 2 meters is going to equal the sine of 30 degrees, which is 1/2. So actually L sub Y prime should equal 1.00 meters, right? Yep. Okay. And that's sine of 30 degrees is 1/2. So we know that part, okay? But L sub X prime is going to equal L sub X divided by gamma. It's shortened along the direction of motion. And so we should be able to figure that out. L sub X will equal gamma times L sub X prime. Oh, and we didn't bother to figure out L sub X prime, did we? L sub x prime over 2.00 meters is going to be the cosine of 30 degrees. And so L sub x prime will equal 2 times the cosine of 30. Which is the square root of 3. I'm going to call it 1.73 meters. Okay, well, I can figure out L sub x prime. I know their relative speed. It's 0.995 c, and I'm going to try to use U's for these things today. Gamma is going to be 1 over the square root of 1 minus. Okay, also I'm going to, beta is the speed divided by the speed of light, and gamma is 1 minus beta squared. That's just a shorter way of writing stuff. That's 0.995. Yeah. Okay. Oh, I didn't see the E1 on the bottom of this thing. Beta is actually going to equal 10.0 for this particular problem. So that L sub x and the rest frame of that thing, it's going to be 10 times the length. It's going to be 17.3 meters. So that's part, well, we haven't figured out the proper length of the rod yet. L will equal the square root of L sub x squared plus L sub y squared. We figured out L sub y up here, it's 1 meter. So it's going to equal the square root of that, 17.3 meters squared. Whoops, already did that. Plus 1.00 meters squared. It's going to be a little bit over 17. I still get 17.3 meters with 3 significant figures. So that extra 1 meter doesn't make a whole lot of difference. Something I can, the orientation angle in the rod's rest frame, I can draw a little picture that'll let us figure that out. And we can call that angle phi here maybe. This will be 1.00 meters, and this will be 17.3 meters. And phi will equal the inverse tangent, the angle for which the tangent is 1.00 meters over 17.3 meters. And phi is going to equal pretty small angle, I think. Yeah, I get 3.3 degrees. 3.31 degrees. Okay, so not much to it. And that wasn't too bad a problem. Let's see, you had to recognize first that in the y direction, things don't change. They're only shortened along their direction of motion. And that the person who sees the rod looking like this is seeing a shortened length in the x direction. That'll be its proper length in the x direction divided by gamma. And so recognizing that, we were able to work through and solve for those things. Okay, I think I've got another few velocity problems, although I don't know that we'll get through all of them today. A certain quasar recedes from Earth at a speed of 0.87 c. A jet of material is ejected from the quasar towards the Earth. Oh, a jet of material ejected from the quasar toward the Earth moves at 0.55 c relative to the quasar. Find the speed of the ejected material relative to the Earth. Okay, a quasar, there are things that were discovered in the 1960s. There was actually a brand of televisions called Quasar for a while back then. But the quasar comes from what they called them at first. It was short for quasi-stellar object. And when people study stars, they pretty much all look like pinpoints out there for one thing, but the stars will have, if you make a graph of their, the light coming from the star and make a graph of intensity as a function of wavelength. Here you'll learn a little bit of astronomy. Well, a little bit anyway. And what they see in the light from the star is it kind of roughly traces out, I'll just draw a dashed line for that, a thermal radiation spectrum, which we didn't really study, but then there'll be dips in it in this thermal radiation spectrum at particular points. And the dips that show up in the light from the star is places where the light leaves the surface of the star, what's called the photosphere, and it's usually a nice, smooth thermal radiation spectrum. But then it has to get through tens of thousands of miles of stellar atmosphere, and the stellar atmosphere absorbs light at particular wavelengths because the atoms in there will absorb light at particular wavelengths. And so you'll have these dips that show up in the spectrum. And those dips correspond to the same places that those atoms that absorbed it would emit light. And we can study that here on Earth. And so you'll see dips for iron and dips for hydrogen and sometimes dips for molecules, like maybe an oxygen or a nitrogen molecule, various things. And you study those dips and you can figure out what's in the element of that star. And in the early 20th century, actually not that early, in the 1920s, a woman who was writing her PhD thesis for astronomy realized that the light coming from the sun had a whole bunch of absorption lines for iron, but that was only because iron has a whole bunch of absorption lines in the visible part of the spectrum, and it's good at absorbing light. But she figured out that what stars are mostly composed of is mostly hydrogen and helium, and everything else shows up as trace elements, including iron. And so mostly they're hydrogen and helium, but that's stars, okay? When they saw these quasi-stellar objects, they saw absorption lines, but they weren't for anything they recognized. They didn't see any things that fit very well with what they knew. And sometimes stars will be moving toward or away from us, and the whole set of absorption lines get shifted to longer wavelengths if it's moving away, or shorter wavelengths if it's moving toward us. But still, there are recognizable patterns. For instance, sodium. If there are sodium atoms in a star's atmosphere, and there doesn't have to be very many, but sodium atoms absorb light at about 589 nanometers, and they have two absorption lines that are really close together. So there isn't anything else that's quite like that. Well, sometimes those absorption lines get shifted a little bit to the right or the left because of motion of the star toward or away from us, but they didn't see those sodium lines. And eventually they realized that the absorption lines from these quasars were shifted so far toward longer wavelengths that the ones that normally occurred in the visible part of the spectrum were entirely out in the infrared part of the spectrum. And the ones they were seeing in the visible part of the spectrum from these quasars actually came from absorption lines that, if they weren't moving, would have been in the ultraviolet part of the spectrum. So, but anyway, they called them quasi-stellar objects before they quite figured out what they were. And then they realized that what they were was galaxies in the very early universe, that because of the expansion of the universe, they're moving away from us at a very high speed, like maybe 0.87 C. Whereas when studying starlight, they were mostly accustomed to seeing things that were moving at very small fractions of the speed of light. So like maybe just a few kilometers per second or a few hundred kilometers per second, but not thousands and thousands of kilometers per second. So that's what we've got here. So let's let the Earth be the fixed reference frame. So S is equal to Earth's frame. And S prime will equal the quasar frame. Now, U is the speed of the quasar relative to the Earth, and it's receding. That means it's moving away. So U in this case will equal 0.87 times the speed of light. A jet of material ejected from the quasar toward the Earth moves at a speed of 0.55 c relative to the quasar. But here's the thing here. We've got Earth here, and we've got the quasar out here moving away at 0.87 c, but the jet of material is being ejected back toward the Earth at 0.55 c, and that's v sub x prime, but it's going to be negative because the positive direction is that way and it's going in the negative direction. So that's v sub x prime. And we want to know the speed of that ejected material relative to the Earth. Well, here's the deal. We want to know v sub x. That would be the speed relative to the unprimed system. And it usually looks like v sub x prime plus u. It always looks like v sub x prime plus u over 1 plus u v sub x prime over c squared. But in this case, we've got u is equal to that, but v sub x prime is negative 0.55 c. So let's plug in the numbers and see what we get. I'd have minus 0.55 c here for v sub x prime plus u, which is 0.87 c. And the numerator would give me the Galilean value, which in this case looks like 0.32 c. But in the bottom, we have that correction factor, which in this case is going to be 1 plus, now since this is in terms of c and this has a c, the c squared is going to divide out, and I'll have 0.87 times minus 0.55. And so whatever that turns out to be. Good. I hadn't turned my calculator on, so I didn't actually put any wrong keystrokes in. They just were useless. Okay, on that bottom, I end up getting 0.52 when I subtract this from 1. So V sub x will end up being 0.32 divided by that answer. 0.61 times the speed of light. So it's faster, almost twice as fast as the non-relativistic expression would predict. So got to be careful with these things. And also be careful with signs. This one had a negative sign with respect to what we were used to. Here's another astronomy one. Astronomy is ripe for relativistic problems. Excuse me. We have two jets of material from the center of a radio galaxy. By the way, a radio galaxy is one that emits a lot of radiation in the radio part of the spectrum. And so they're well studied with radio telescopes. They fly away in opposite directions. Both jets move at 0.75 c relative to the galaxy. Determine the speed of one jet relative to the other. Okay, well, let's see. What could we use as the, we can set up our coordinate system in various ways. Yeah, I think this will work. Here's our galaxy, and we'll let, just imagine that it's at rest in space. So, and for one of the coordinate systems, we'll take this jet of material that's heading in this direction at 0.75 c. And this will become, here's our S coordinate system. This will become our S prime coordinate system. And then the other jet going in this direction has a V sub x, which is, this is going to be U. Okay, V sub x is going to be minus 0.75 c for the velocity of this thing with respect to the radio galaxy, because it says these speeds are at 0.75 c relative to the galaxy. And we would like to know what's the speed of this jet with respect to this jet, our U coordinate system. So we want to know V sub x prime. And our expression for V sub x prime is that it's V sub x minus U divided by 1 minus U V sub x over c squared. And we have to be really careful here. U in this case is positive 0.75 c. V sub x is negative 0.75 c. So what this numerator looks like is minus 0.75 c minus U, which is minus 0.75 c. And between the two of those, that's minus 1.50 c. That's the non-relativistic answer, the Galilean answer, which says that this batch of stuff would be moving away from this batch of stuff at 1.5 times the speed of light in the negative direction. However, we have to divide by that correction factor, which is going to be 1 minus U is 0.75 c. V sub x is minus 0.75 c. And with that minus and that minus, this is going to be 1 plus 0.75 squared. And on the bottom, I've got c squared. So the c's divide out, as they will, as long as we determine these speeds with respect to the speed of light. And I'll have minus 1.50 c divided by 1 plus 0.75 squared. So let's figure out what's the speed of one of those. And we'll stop after this one. V sub x prime. As is often the case, I had to recalculate this. I get minus 0.96 times the speed of light. So the speed of this thing, which the Galilean prediction is 1.5 times the speed of light, but it's minus 0.96 times the speed of light. So that one worked out. Okay, and I think, yeah, I've got some more kind of space kind of things that we can work on tomorrow. And there'll be some more problems with these Lorentzian transformations, especially the velocity transforms. So, okay, I'll stop recording here.